Hello everybody and welcome to exercise 7, and this is going to be an exercise in finding volumes of solids of revolution. And we're going to do this in 3 videos because there are 3 parts to this problem. And the first part of it is asking us to find the volume of the solid region that we get if we rotate the region bounded between the line y equals x and the parabola y equals x squared about the x-axis. Okay, so this refers to figure A. Okay, notice that in that figure the 2 curves have been drawn for us, and so the region they're talking about is this part that I'm shading here between the line and the parabola. We'd like to take that and rotate it about the x-axis. All right, so let's draw just a second picture of this that's a little bit bigger, just to make this easier to think about. Okay, so I'm going to first redraw the line and the parabola. Okay, and remember, we want to rotate that about the x-axis, so that region that I just drew is going to come out down below. So if we draw its mirror image, okay, I'm going to do my best to draw that. It would kind of look like that. All right, and the strategy for finding a volume of something like this is to do it in slices. Okay, so imagine taking out a big machete, and we're going to slice this solid region that we've drawn perpendicular to the axis of rotation. Okay, if we do that, we're going to be going top to bottom, and we're going to slice through this region. Notice that there's a big hole in the middle, and so what we're going to get is a washer type of a shape. Okay, something like that. Okay, and the key to setting up the volume integral is to come up with an expression for the area of that washer that we just drew. Okay, so I'm going to go over here to the right and kind of draw a front view of that washer. Okay, and the key to getting the cross-sectional area of that washer is to figure out what these 2 radii are that I'm drawing. Okay, so if you go back to the picture, that smaller radius, the inner one, the distance from here to here, in our picture that would be this distance. And my first question to you is that a vertical or a horizontal distance that I just drew in green there? Okay, you can look at that and see that it's vertical. That tells us that we need to solve our equations for y, basically. Okay, so what we're interested in knowing is what's y equal to here and here. That's going to ultimately help us find those 2 radii. You can go back to the statement of the problem. Let's scroll up a little bit and see that one of the y's was x squared. Okay, that was the parabola, and the other one was x. All right, so going back to our picture then, over here to the right, this front view that we drew, we can now look at the picture and see that the inner radius, the shorter one, is just the distance from y equals x squared to the x-axis. That's just going to be x squared minus 0. Okay, and then what about the bigger radius? Well, that would be the distance from the x-axis all the way up to our upper curve. That's going to be given by y equals x. Okay, and so if we want to write down a formula for the area of this slice, okay, we just need to take the area of the bigger circle minus the area of the smaller one. So we're going to get pi times the bigger radius squared minus pi times the smaller radius squared. Okay, so there's a formula for the cross-sectional area. And last step then is to get the volume by adding up our cross-sectional areas from left to right. So imagine taking these washers one at a time, stacking them together from left to right, and doing an integral to get the total volume of the region. Okay, there's only one problem here. Do you see what's missing from our integral? We don't know what our limits of integration are yet. Okay, so we need to figure out what our points of intersection are. Okay, so where do these 2 curves cross each other? I'm trying to see if there's a place where we can sneak that calculation in. Okay, let's maybe sneak it right here. Okay, so points of intersection, we're just going to take the x and the x squared and set them equal to each other. Okay, so if we take that, just subtract the x from both sides, notice that we can factor an x out of there. And what we wind up with is either x equals 0 or x equals 1. Okay, and so we have just discovered that our limits of integration must be 0 to 1. Let's fill those in on our integral. And we're essentially done. Okay, they just asked us to set up this integral and not evaluate it. We could do a little simplification here. So pi x squared minus pi x squared squared is x to the 4th. Okay, and that integral then represents the volume that they were asking us for.